Okay, so we are still on hybridization, the concept of hybridization. Let's look at bond angles. So what is a bond angle? So we are told it is the internal angle of intersection between two lines drawn through the nucleus of a central atom from the nuclei, that's plural of nucleus, of two atoms bonded to it, right? So bond angle. So the center from one nucleus to the other, right? That's the bond angle. It's a line drawn. So you have this. This line, right? The angle can be here, right? Bond angle. Factors affecting bond angles. The type of hybrid orbitals used in bonding. Yes. So if you are using sp3, you have 109.5 degree. If you are using sp, you have 180. If you are using sp2, you are going to get what? 120 degree. So the type of hybrid orbital you are using affects the bond angle. Yes. The number of orbitals occupied by electron pairs in the valence shell of the central atom. So you check your central atom. If the number of electron pairs are present, right? So we have some electron pairs present in the central atom, can also affect the bond angle. If you don't have them, it will also account for something. Now, when you pick CH4, methane, the central atom carbon does not have any lone pair there, so it is 109. Now, when you pick NS3 compounds, they look like this sp3, right? They are even sp3 in a sense, but the central atom is occupied by a lone pair. So something will definitely happen, right? So the number of orbitals occupied by the electron pair is also what? A factor. Example, in NS3 compounds, where S can be hydrogen or halogen. So ammonia, NF3, NCO3 are our examples here. The central N atom is sp3. Yes. But this one does not have a bond angle of 109.5 degree and a tetrahedral shape. Why? Reason. One of the sp3 hybrid orbital of N is occupied by a lone pair of electrons. So the axis of orbital has a tetrahedral shape, but the lone pair electrons prepare the bonding pair, right? And as a result, we close the bond angle towards 107 degree with a trigonal pyramidal shape. What are we talking about? Illustration. So consider NH3, ammonia, right? Good. So there's ammonia, and ammonium is right. So the ground state configuration, ground state electronic configuration. Nitrogen is 7, right? We have 1s2, 2s2, 2px, 2py, 2pz. So this is 2, 4, 5, 6, 7. Good. Now there's a ground state. You aside from the 2s into any of the empty orbitals here, right? Now the orbitals to accommodate our food. Fine. So what we are seeing here is that this thing here becomes what we call a lone pair. Right? Lone pair. Good. That's a lone pair, right? So we can form our sp3 already. S1, 2, 3. So sp3. But the presence of this lone pair, right, is causing the bond angle to change. So what happens is that if you have this as nitrogen, right? So you have this. Now the lone pair is here. Now in natural sense, this thing here, they are somewhere here like that, right? In this spatial orientation. Now, this lone pair electrons repel these bond pairs. Let's push them. So as a result, right, trying to occupy another space, right? So when they are pushing them, so they reduce this angle to 107. That is how come ammonia has a bond angle of what? 107 degree, right? So now, each sp3 hybrid orbital, this is sp3, okay, will now overlap easily with what? The s orbital of hydrogen atom to form sp3s, nitrogen, hydrogen, sigma bond. Are you okay? Good. So there is a formation of ammonia. So take note. So it combines with this, as you can see, right? That is real. But the presence of this lone pair repair the bond pairs. And repair the bond pair. It closes the angle to 107. So explain why ammonia although the central atom appears to be sp3, it does not have a bond angle of 109. There isn't. You have to write this configuration and to do some demonstration here, right? So the presence of the lone pair of electrons, right, repair the bond pairs and closes the 109.5 degree angle to what? 107 degree and changes the shape to what we call what? Trigonal pyramidal shape. Are you okay? Good. So what made ammonia so is the lone pair of electrons. Are you okay? Good. Now you look at a similar one with what? Water. So that is it. Good. Now, so in our discussion, right, as I said, so you see one of the hybrid orbital is occupied by a lone pair. Take note. The central atom here is sp3. So you expect to get 4. 1, 2, 3, 4, right? So one of them is occupied by a lone pair. That is why you see it like that, right? Good. Now let's go to water. In water, or in H2O, the central oxygen atom is sp3. Good. With the two of its hybrid orbitals occupied by lone pair electrons. As a result, the two lone pair repair themselves and also repair the bonding pair, thereby closing the angle to 104.5. So because of that, water is not linear. You see, water appears to be linear. You just want to look at it like this. You just want to look at it like this. You see, water is not linear. So water is supposed to be linear. I see two of its hybrid orbitals is occupied by two lone pairs. So this lone pair repair themselves. So in the course of going the other side, they attack the bond pair. This also attack the bond pair after leaving the brother here. So they close the angle. So it appears that it becomes something like this. I think I changed it right? There is this. Okay, you see? So it closes it. So water at the end happens to be this. Can be a fit. Are you okay? Okay, let me demonstrate with the clouds. Let's go. So the oxygen atom here, 1s2, 2s2, 2px, 2py, 2pz, 2, 2, 4. There's 2, 1, 1, 1, right? There's 7, right? So have this. Now we have two lone pairs. Do you agree? These are what we call the lone pairs. So you see, oxygen central atom has two lone pairs. Good. So what will happen is that it's supposed to be linear, as you see here. It's supposed to be linear, like this. Because it's clear, you can see that, right? But you have been told that water is not linear. And the reason is what you are stating. So these two lone pairs repair themselves. After repulsion, they go apart because you are repelling. They don't come together again. So they attack the bond pair, and closes it. So water linear happens to have a V shape after what you are saying. So they is supposed to be the shape of water. Yes, no argument about it, right? That is why it does not have a linear shape. Are you okay? Good. So you have this. So these are all hybrid orbital, but just that two of its hybrid orbital is occupied by lone pair. Are you okay? Good. So what happens is that I'm going to form something like this. So see, these two, they repair themselves, right? After repelling themselves, what will happen is that they also repair the bond pairs. So they close that linear shape to this. So you happen to get what we call 104.5. So water has what we call bent angular or V shape. You see the bond angle, the distance drawn from the nuclei of the two atoms. You see that? It's a line. So at the end, you get this. After repulsion, you don't expect them to be here, or see them here. Good. Application. Explain why water is not a linear molecule. You explain by writing this configuration, telling us about the presence of the two lone pairs, as you can see in the drawing, right? In the configuration, and telling us why it is not linear. So two of its hybrid orbital, you see there is 1, 2. It's supposed to be 4, 1, 2, 3, 4, right? So two of its orbital is occupied by what? Two lone pairs. So because of that, the lone pair repair themselves as well as the bond pair. So after repulsion, it closes the angle to 104.5 degrees. That is why water has what we call a V shape. Okay? Good. Let's look at another application here. So what we just discussed, CH4, NH3, and water, these two are all described as having 4 electron pairs linked to their central atom. Yet, their respective bond angles are 109, 107, and 105. Account for the difference in the bond angle. Yes, they all appear to be sp3, showing characteristics that the central atom here, central atom there. But their bond angles are different. Explain. We refer to those, what we just discussed. Are you okay? So that is how it goes. So you pick this. Why is it 109? You go to sp3 concept. Then you come here. Why is it 107? Then you go to the trigonal pyramidal shape concept, right? What I just said. An appearance of just a lone pair. Good. Here, they have 2 lone pairs. Lone pair, 2. So you explain, right? From the same concept. So that is it. Welcome to dipole moment. Dipole moment is the product of the charges and the distance between the 2 charges in any polar molecule. So the unit is thereby, or kilometer. Right? That means compounds. So when you have ACl, HF, and the rest, you see carbon exhibits what we call tetravalency, okay? That's why I say double bond here, okay? Okay, so you can hardly see carbon dioxide like this. See carbon dioxide. And you see something like this. No. 4 bonds surrounds a carbon. Are you okay? So the tetravalency concept will make it like this. Are you okay? So that is how you are seeing that, okay? That is one side of the molecule, that's carbon monoxide. So all the things you see here are polar. Why? And they have a net dipole due to the difference in electronegativity between the 2 atoms. So you see chlorine is more electronegative than this. So there can be a dipole moment. You see the direction is on the chlorine. Chlorine is pulling electron to itself, okay? So there is what we call separation of charges. So hydrogen happens to get a partial positive charge and there's a partial negative charge. Are you okay? This one, so oxygen is more electronegative. It pulls the electron more to itself, right? So the difference in electronegativity accounts for the reason why it has a net dipole. Okay? Dipole is a product of the charges and the distance between the 2 charges in any polar molecule. Okay? What makes them polar? The plus and minus. You remember? MS2 compounds. Now those with linear shapes such as this are not polar. And why? They don't have any dipole moments. Even if they have a 0, so they don't have. That is because the individual bonds do polar. Yes. The bonds seem to be polarized. Oxygen, see, do polar. Good. Move in opposite direction and so cancel out. Yes, this is polar. That's true. You have a dipole moment. The dipole moments work in polar molecules, and this is polar. But it goes that way. It also goes that way, opposite direction, so they cancel out. They cancel out and they end up with a 0 dipole. Yes, they are polar, but they ended up with a 0 dipole because they moved in the opposite direction. Are you okay? So it has no dipole moment. This one also does not possess any dipole moment, right? Because chlorine pulls electron partial negative. This is very a partial positive, right? There are separation of charges because we are pulling. This one also pulls, they cancel out, right? That's the cancellation. Okay. Good. But let's continue here. Those with the bent or V shape are polar because they are unsymmetrical and the individual bond polarities do not cancel out. They have a net dipole. Now, symmetry. Like humans, we are bilaterally symmetrical. See, a line we divide something to halves, equal halves, right? So when you divide me, I have only one line of symmetry, okay? So you get here, right? Good. So they say this molecule here, they are unsymmetrical. So they are unsymmetrical, so the bond polarities do not cancel out. So they have a net dipole. Why do we say they are unsymmetrical? Okay. You want to divide this to get equal halves. You don't know how you're going to do it, right? So they're unsymmetrical molecules. So all these ones are unsymmetrical molecules. So they don't cancel out, right? So they retain their dipole moments. So they have a net dipole. So if you cancel out your dipole. Now, The first one has a dipole moment because of the electronegativity, right? Chlorine pulls more to itself. Good. So that is why we have the separation of charges. Partial negative, partial positive, right? So even if unsymmetrical molecule, yeah. So this, yes, they're all symmetrical molecules, so they don't have that. Now let's look at the last one. Let's look at the last one. Let's check on this. Symmetrical and unsymmetrical nature of something. So they said this one do not, or duopolar. Okay, those with bend shape are unsymmetrical, and the molecules do not cancel out, right? So this partial positive, right? If here direction was also supposed to be partial positive, like they will cancel out. So this is unsymmetrical. You see, when you divide them, you should get the same thing here, here, and there, right? Good. Now let's watch this one. MS3 compounds. Those with trigonal pyramidal shapes are non-polar. They have a zero dipole because the molecule is symmetrical, and so the individual bond polarities cancel out. All BS3 compounds. Example here, very long one right here. Let's go. So there is chlorine, chlorine, chlorine. The direction here pulling electron, electron, electron there. You see, this is symmetrical. So the bond polarities cancel out, right? So it makes them what? Have a net dipole of zero. And if they don't cancel out, you don't get a net dipole of zero. So all in all, one, the MS compounds, that's ACl, are polar, so they have a net dipole. MS2 compounds, as you saw here, they say they have a net dipole of zero. Why? Because the individual bond polarities, although polar, cancel out. So when you cancel out, you don't have. Now when you go to MS3, they have a MS3 compounds here, right? They also have a zero dipole. Why? The molecule appears to be symmetrical, right? See, three directions. So the individual bond polarities cancel out. It makes them non-polar, as you saw, and also have a dipole of zero. Now, those with the trigonal pyramidal shape, they have a net dipole. Why? The molecule is unsymmetrical. So take note, unsymmetrical molecules have dipole moments. Symmetricals don't have. Why is that symmetricals don't have? Symmetrical, right? You have, when you divide, you get equal halves. So since they all move in opposite direction, they cancel out. MS compounds have. That is it. Now, this one also is polar, but it doesn't have a dipole moment. Why? You can see them move in opposite directions, so the bond polarities cancel out. You take negative here, take negative there. So they cancel out. But now, watch. You take negative here. I have positive here. What is cancelling out here? I hope you are getting it. Now, you pull negative here, negative here. They'll cancel out. So this one is unsymmetrical, as you can see. Negative going here, positive, positive. What cancellation is here to be done? I hope you are getting it. What goes to the left, if it's going to the right, fine. It's going to be cancelled. That's why they call this unsymmetrical. Are you okay? Now, symmetrical. It's not about circle or anything. It's just a line we divide something into equal halves, okay? That's what we call symmetry. Good, so they're symmetrical. Now, trigonal pyramidal, you know that, like ammonia. Ammonia, right? Ammonia is also unsymmetrical. The shape of ammonia is also unsymmetrical, right? Clean that shape. Ammonia is also unsymmetrical, right? Good. So this is partial steps, unsymmetrical. So they have a dipole moment. Now the last one, MS compounds, they are symmetrical. As usual. If you are symmetrical, then you can have a dipole moment, right? Good. Now that is the end of this topic hybridization. Thank you for making time with us. And don't forget to subscribe. We entreat all of you to do that if you have not done that. Good.